Hey everyone, you might have seen many videos regarding alternating voltage or current, but believe me, today we are diving practically deep into the world of alternating current or AC voltage. Why frequency is transmitted at 50 Hz and 60 Hz only across the globe? There should be some reason behind it. Let us today transmit AC voltage at the frequency as low as 1 Hz, 2 Hz, 5 Hz, or even 10 Hz and see what happens to the electron movement when we are dealing with the different frequencies. How actually the AC wave travels in the transmission line and how it reaches our homes, industries, etc. Let's visualize AC voltage and frequency with an oscilloscope. The late 19th century was a time of incredible change. The world was entering a new era, and this era was powered by electricity. Electricity promised to illuminate homes and power industries. At the forefront of this revolution were two brilliant minds. They were Thomas Alva Edison and Nikola Tesla. These inventors would shape the future of how we use energy, giants of electricity. Thomas Alva Edison was already a renowned inventor. He was famous for his work on the phonograph and the incandescent light lamp. Edison championed a system called the direct current or DC. On the other hand, Nikola Tesla, a brilliant Serbian American engineer, later joined Edison's company. Tesla had a different vision. He believed in the potential of alternating current or AC. Direct current flows in one direction, while alternating current reverses direction periodically. Electricity is all about the flow of tiny particles called electrons. Voltage and the frequency are two important ways we measure this flow. Let us visualize AC voltage and frequency with an oscilloscope. As I have connected two LEDs, one red which is for the positive half of the sine wave and green LED which is for the negative half of the sine wave. Voltage is like the peak of the wave, how high the wave is, and the frequency measures how often the direction of the wave flow changes. It is measured in hertz, which means cycles per second. In a typical AC circuit, electron oscillates back and forth, driven by the alternating current. As the standard around the world is 50 Hz and 60 Hz, this oscillation happens 50 or 60 times per second. Now what happens if we give lower frequency like 1 Hz, 2 Hz, 5 Hz, 10 Hz, etc. As I have given the frequency here, that is 0.1 Hz, that means an electron completes one cycle in 10 seconds. That means half cycle completes in 5 seconds. You can observe at positive peak of the wave, red LED glows, and when the sine wave starts falling towards zero crossing, you can observe no LED glows, and when the negative peak of the wave reaches, green LED glows, then again starts rising towards zero crossing. You can see near zero crossing, no LED glows, and this way the sine wave travels. Now similarly, if we give 1 Hz, that means in 1 second, one cycle gets completed. You can observe at positive peak of the wave, red LED glows, similarly at the negative peak, green LED glows, and at zero crossing, no LED glows. This slower oscillation means that each electron travels a bit further in one direction before reversing. Now similarly, we will give 5 Hz, and the effect becomes more pronounced. The electrons now reverse the direction in just 5 seconds per second. That means in 1 second, 5 cycles gets completed. This results in an even more extended travel path before they switch direction again. They still oscillate around the same spot because the movement is all about back and forth motion. The overall energy transfer remains constant, just spread over a longer period. Imagine if this would have been the standard frequency as low as 5 or 10 Hz, as the slower oscillations can have practical impacts, especially in devices sensitive to frequency changes. You might have observed how the flickering of the bulb would have happened or how the motor would have turbulence. One key characteristic of low frequency AC is that its wavelength is much longer. For instance, at 10 Hz, the wavelength is about 30,000 kilometers. This means that the electric current changes direction very slowly compared to higher frequencies. So what does this mean for practical applications? Firstly, low frequency AC is less efficient for transmitting power over long distances. The slower alternation increases losses due to reactions in the transmission line. This is why the power grid operates at much higher frequencies like 50 Hz or 60 Hz. However, low frequency AC has its own advantages. For example, it's often used in grounding systems and in some types of signal processing and audio equipments. The slower cycle can help in controlling noise and interference in sensitive applications. Another interesting point is the skin effect. At lower frequencies, the AC current tends to penetrate deeper into the conductor rather than just skimming the surface. This can have implications for the design of transformers and inductors, where the distribution of current within the wire becomes more uniform and at lower frequencies. So next time you are working on project that involves AC voltage, just don't think about standard frequencies. Consider how low frequency AC would impact your design and performance. Understanding both voltage and frequency is key to understanding how electricity works and how to stay safe around it. Some people think low frequency electricity is safer than higher frequency electricity, but this isn't always true. Remember, voltage is like the pressure pushing the electrons. Even at low frequencies, higher voltage can be extremely dangerous. Think of it like a slow moving but powerful river. Just because the water isn't moving quickly doesn't mean this can't sweep you away. Low frequency electricity can have different effects on the human body than high frequency electricity. Our bodies use electrical signals for many things, like controlling our heartbeat. Low frequency electricity can interfere with these signals, causing serious health problems. For example, exposure to high voltage at low frequency can cause muscle contraction, burns, and even heart problems. That is why it is so important that to treat all high voltage situations with extreme caution. The most important thing to remember is that high voltage is dangerous regardless of the frequency. Always assume that electrical equipment is live and never touch exposed wires. If you are working with electrical equipments, always make sure it is properly grounded and use insulated tools. Also, the question arises, why 50 or 60 Hz only? The choice of frequency was not entirely scientific at the first. It was influenced by trial, error, and the technical constraints of the time. 50 and 60 Hz were chosen because these frequencies represent a good compromise between two factors, electrical power generation and mechanical efficiency. Earlier generators were mechanical devices, often driven by steam engines, water turbines, or other mechanical means. Generators needed to rotate at a speed that could efficiently generate AC while maintaining mechanical stability. At 50 or 60 Hz, the speed of the generator's rotation and the number of poles in the generator was practical for the technologies available. So alright, that is for today. If you learned something new, hit that like button and subscribe for more engineering insight. Thanks for watching.